So guys, obviously right now we are playing catch up, that we're sort of making this up as we go. Chances are good you guys didn't see these emails yesterday, but your parents and your teachers did. So I just want to explain to you what's going on, what I know, with the understanding that all of this could be changing. So what we know is this. Yesterday we crossed a threshold that demanded that we implement test-to-stay protocols. Understand that this is not something that's been instituted by state health. This is not something that's been instituted by the CDC. This is actually state legislation. At the end of what we thought was the end of COVID crazy, last spring, the state legislators got together and they started to think about and pass laws about how to manage what we were thinking might be future epidemics. And then we find out quickly that this wasn't over. But what the legislators did is they withdrew a lot of the governing power over how we respond as a society to pandemics, and they instead instituted some rules. And one of those rules says, in order for schools to stay in session, if you are a school smaller than 1,500 students, if you have 30 kids that simultaneously have COVID or any other communicable disease, you have to institute what's called a test-to-stay program. Then if you're a school bigger than 1,500, it's 2%, but that doesn't apply to us. So, guys, yesterday we hit that 2%, or I'm sorry, that 30 student limit. Then things got confusing because the CDC, well, not the CDC rules, but there's another group thinking about this, the physicians and doctors and epidemiologists, even at the state level. And they were initially saying, if you've had COVID recently or if you are fully vaccinated, then you don't have to test. And so an email went out a couple days ago that said, if you're vaccinated or recently recovered, you don't need to test. Then they started to muck around in the law, which is actually driving this process, and the law says everybody tests. So an email went out 2 days ago that said, we hit 30, we need to test, because actually we hit 30 2 days ago. We need to test, but if you've been vaccinated, you don't test. Then we looked at the law and we said, oh shoot, no, that's not the case. So we had to send out another email. This went out yesterday afternoon that said everybody tests, and that's going to happen next Wednesday. Then what happened was the district leadership started to look at how other schools were handling this. And up in Canyon's district, they're doing something completely different. Today is the last day of second quarter up in Canyon's district. Their second quarter goes after Christmas break. And so they have Monday off because it's Martin Luther King. They have Friday off because they give their teachers, we do minimal days. They do complete days off. So they have Friday and Monday off. So what they thought in Canyon's district is if we give students Tuesday off, then that would give us Friday, Saturday, Sunday, Monday, Tuesday, which is a 5-day quarantine period. So they got creative with this, and they said if we can just cancel school for 5 days, which up there only means one additional day off, then that could be a quarantine period. Maybe that would reset the COVID count clock, and maybe we won't have to do a test to stay. Does that make sense? So Alpine School District saw this idea and they jumped on it. They were like, hey, maybe we could do that too. And so guys, please be really careful about what you're hearing. So we don't have school Friday, we don't have school Tuesday, giving us the same 5 days off. We don't know, neither does Canyons, but we do not know if that's going to satisfy the requirements to avoid a test to stay on Wednesday. So the current plan is that we will come back on Wednesday to our short day, and that will be a test to stay day where they will COVID test everybody in the school, regardless of vaccination or recovery status. Everybody in the school will get tested. And the way this is going to go is right now we think we're going to do it down in the gym. Some schools are going to do it as drive-up not in our district, but we're looking at doing it in the gym. You'll need to register onto the same site that you had to register for last year, which is when athletes had to test to play. You'll be on there, you get registered, you come down. It's not the brain tickler, it's not the PCR deep swab, it's a superficial swab, it's an antigen test. Results are back in 20 minutes, and literally what they're going to do, we think right now, is they're going to swab you and then have you sit in the bleachers, and when your results are back, if you're clear, you'll go back to class. If you throw a positive test, you will immediately start your 5-day quarantine. Understand that if you choose not to test, we're going to assume that you're positive and you will have to quarantine. Yeah.
So you were saying it stays off, and other teachers have set distance.
No. And actually, as I said that, I realized I needed to back up on that. It's technically distance learning. Sorry, those weren't precise words. You're right. It is distance learning, but it's, when I said days off, I meant days not in school. Off wasn't the right word to use there. So they are distance learning days, and so. But guys, understand again, we're being really flexible here, right? Because we don't know what's going to happen. That's why I ran downstairs and I was a minute late to class. I went down to ask administration if we knew anything more about Wednesday, our test to stay day. Currently, the plan is that it will be a test to stay day, largely because we don't know how the governing bodies are going to think about or respond to our 5-day out of school, not days off, but still not together days, from tomorrow through Tuesday. Yeah. Yeah, so, yeah, right? That's a good question. It's probably going to feel a lot like that day that we have typically in September when we do school pictures. Would everybody from A to C come down to the gym? You know what I'm talking about? It'll feel a lot like that. We have no idea how many people are going to throw positive tests. Right now, the positivity rate for all tests is about 30%, which is quite high. But understand that those are the people that are choosing to be tested, and those are typically the people that have symptoms. And so 30% right now of the people in the state that are getting tested throw a positive test. We're hoping that our percentages will be significantly lower than that, simply because we're testing everybody and not just people that are symptomatic, but we don't know. But we're going to see the number of people in this building decrease over the day on Wednesday as we get through the day. So, yeah. Guys, so do you have any other questions about, I'm telling you everything I know. Please, though, guys, be really careful about what you're then going to tell your friends. I'm being super transparent with you. I'm glad that Kale called into question what I said. It is not days off. Friday and Tuesday are distance learning days. Your teachers will, on a class-by-class basis, decide what that means. But it is online learning. I'll tell you in a minute what we're going to do. But it is online learning days. So, guys, other questions about, I'll do my best to answer given the limited information that I have. You guys okay? Last thing then, don't be surprised if things change between 2 and 11 times between now and next Wednesday. The only thing that we know for sure right now is that you will not be back in this building unless you're an athlete or involved in some other extracurricular thing. Oh, I should say, because right now, guys, before I went to bed last night, the latest news is that activities and athletics are still happening. That said, your meet got canceled, right? Okay, so the official stand is that athletics are still happening. Talk with your coaches, talk with your activity advisors, but they at least haven't shut those things down. We have a wrestling match tonight, and I have no idea whether we're doing it or not, so I don't know. So guys, any other general questions? Okay, so let's talk about the calendar really quickly. During this unit that we're now involved in, which is all about molecules, polarity, intermolecular forces, and today we're going to talk about how these molecules play together in large groups. Guys, in the middle of not in the middle, but somewhere in this unit, we like to throw in a day where we watch a video. It's done by PBS, it's done by Nova. Specifically, it's a guy named David Pogue, who is super bright and really interesting. But the name of the video is Making Stuff Colder. It's fascinating. It's all about what happens when things get really cold. This year, frankly, we were planning on not doing the video simply because these have been crazy days and we just thought we could buy back an extra day in the year. So initially we decided we weren't going to do the video this year. But then we found out that Wednesday, as David got us thinking, is going to be kind of a crazy day. And so we decided to put the video back in simply because if we do test to stay, Wednesday is going to be a weird day. So with that said, especially because right now it's really important to Miss Call and I that we keep A days in front of B days because we're working with a student teacher, and it's really important that Mr. Brown see me and Miss Call teach before he goes to try to teach. Before he teaches. Sorry, that wasn't right. Guys, we got to keep A days before B days. So what that means is that Tuesday was going to be a day where we were going to watch a video, the same one they'd watch B day. That's no longer the case. But guys, it then really complicates the schedule. So I sat down last night at about 11 o'clock to try to reorganize our calendar, and it blew up in my face. There were so many variables that I didn't know the answers to that I couldn't move forward. Here are the things that we know, and these are some things that you should understand. So guys, we know this. We know that we are no longer watching a video on Tuesday because we don't have school on Tuesday. And so your deal on Tuesday is not going to be to watch that video as a distance learning activity. Simply because we want to keep that video, and I'll just be straight with you, as a way to burn a day, depending on what happens with the other days. So that is not what you're doing from home on Tuesday. Currently, we are going to keep this as a video day, simply because we don't know what's happening with Wednesday. And then, guys, we're just going to go on from there. The thing that I can tell you for sure, so just keep your eye on the calendar. What do we come back to? Is it an A day? No, they're not messing up the A day, B day calendar, because we're going to miss a B day and then an A day. So we'll come back to a B day. So guys, the next time that I will see you is a week from now, next Thursday. And just come, we'll figure it out. It'll be fine. By the way, if we do test to stay on Wednesday and you throw a positive test, let's talk about what to do. Guys, you don't need to try to submit work to me from home. We're not going to do that. What the expectation is if you do throw a positive test and you're at home, you'll be working from home. So there's a very real chance that you're still going to miss this lab. You will print the lab sheet. You will watch the pre-lab screencast, and then you will watch the video of the lab, and you will collect data and write it up as if you were in class. If you miss a day of lecture, you watch the screencast, you do the homework as if you were in class. You've already got the homework in the homework packet. Don't try to turn in any of that stuff from home. Just bring it back with you when you return, and we'll take care of it then. But guys, the expectation is you're going to stay caught up from home. Now understand again that this is only if you throw a positive test on Wednesday and you're homesick. This is not my expectation for Friday or Tuesday. So guys, any questions about that? Is that okay? Okay, so now let's talk about all of us, regardless of testing status. Guys, first of all, we can no longer do a essentials remediation day. on Tuesday because we're not in school on Tuesday. So what we're going to do is we're just going to burn that remediation day, and that means we're going to have 1 day of remediation on Thursday, and then the essentials test is also then going to be on Friday. So all we're going to do is we're going to get rid of that 1 day of remediation. The rest of the schedule doesn't change. If Thursday does not work for you for that remediation day, the expectation is you'll come and talk with me. Otherwise, if you're doing remediation and you miss it, you just missed it. So come and talk with me ahead of time. Also, guys, your nuclear papers are supposed to be due on Friday. We're going to push that back to Friday the 28th. Simply because we don't know what these days are going to look like. So don't try to get your papers done, your rewrites done by the 21st. We're going to push those back to the 28th. Questions now? Okay, then one last thing to say. Guys, what are the expectations for you working from home over this period of time? And the answer is this. Guys, the material that we are doing right now in this class does not transfer well to at-home learning. It's very visual, it's very hands-on, and you know if you've ever watched a screencast, if there's stuff going on up here on the that's not on the screen, you can probably figure out what's going on, but it's not ideal. And so, guys, consequently, if you are at home, well, when we're at home, I guess for us that would be next Tuesday, we do not have expectations that you're watching a screencast or doing homework or anything like that. So what are the expectations in chemistry for these online learning days? And guys, it's simply this. If you are... Apparently I can't click. Guys, when we're at home on that Tuesday, you only in this class have stuff to do if you're doing remediation. So simply, if you're at home, the expectation, as it says here, is please use your time over the extended weekend to complete remediation steps 1 through 3. Because of missed school days, we'll only have one remediation session on Thursday, and then the essentials test on Friday. So because we're losing that additional remediation time, the only expectation we have for you from home is that if you're doing remediation, you come back with this stuff done when I see you on Thursday. Other than that, you have no other expectations from this class from home. Does that make sense? Okay. But as Cale said, that doesn't mean that's the case in all of your classes. It's just what we're choosing to do with our time in here. So, guys, that was a lot of stuff. I'm trying to tell you everything that I know, again, with the expectation that things are going to change. But not in this class. This is what we're doing. So even if Wednesday's not a test to stay, this is what we're going to do. Kelly, you okay? Are we okay, y'all? Are we good? Okay. So, guys, with that said, let's just transition cleanly and quickly into looking over our homework. Let me get rid of this. No, I need to keep that. Let me grab this. And, guys, turn to homework assignment number 2-3. That's the wrong one. Got to quit this. And guys, let's step through this. Let's talk about the stuff that you need to be clear on. Guys, please ask questions as we go. And then we're going to jump then into what we're doing today. So guys, hopefully you remember that there was a vertical line that separated your homework into a 2/3 side and a 1/3 side, and you only needed to do the stuff on the left-hand side of that line, but you were not able to do things like 1 and 3 and 6 because those were blank and you had no information to base your thinking on. So guys, what I did then in making up this key is I circled the information that was already there. So guys, we can certainly talk about details, but I'd like to talk about principles. So guys, if we have a molecule with a low polarity, will its intermolecular forces be weak or strong? You guys okay with that? Low polarity, low imbalance, low magnetism, if you will, and as a result, low stickiness, and stickiness are the intermolecular forces. So guys, the idea is this. Water is actually a highly polar molecule, and so these things work like little magnets. This is the negative end because oxygen's more electronegative than hydrogen. So this is the negative end. This is the positive end of the dipole. They stick together, positive to negative, and we understand, guys, that stickiness, just think stickiness, guys, that stickiness we call intermolecular forces, forces between molecules. But if you're thinking stickiness, and then you can write IMF when you think stinkiness, you're good to go. Is that okay? So guys, what about this? What if we have a molecule that has a high polarity? What will be true of its stickiness? High stickiness. But guys, you've also got to understand that it goes both directions. Not only does polarity tell us the strength of the IMF, but if we know the strength of the IMF, we know the polarity. So if you've got a molecule with high stickiness, it will be very polar. And if you have a molecule with low stickiness, it will have a low polarity. So these relationships go in both directions. Do you need any clarification on that? Is that crystal clear? Because that's important today. So guys, why is that important today? And the answer is this. Today what we're going to do, guys, is we're going to talk about the so whats. What does it matter if a molecule is really sticky? And we're going to talk about what does that do to the temperature at which it boils? What does that do to its volatility? And you don't even know what that means yet. But guys, we're also going to talk about what does that do to its adhesive and cohesive forces, and that's where we're going today. So guys, fundamentally, you got to be clear on this. Molecules with high polarity are really sticky and vice versa, and it goes in both directions. You guys good? Okay, so now guys, do this with me. If you understand that concept, let me ask you this question. Why did you circle? Not which ones did you circle, but why did we have you circle the most polar molecule in each one of these pairs? What would be the significance of us having you do that now that you understand where we're headed with this? Go ahead, Ami. And therefore, and that's where we're going. And you don't know the answer to that therefore, but I cut you off. Your earrings are really cool.
Thank you.
Do they keep your mask on?
Well, my mask is under it.
Like if your mask was to come undone, you'd rip your ears off. Like it would grab that earring and Kimball's going, wait, what's going on? All right. But Ami, you're exactly on it. Can you guys all go where Ami's brain just went? Because this is the connection. If we know the one that's, if we know the one that's the most polar, we also know the one that has the stronger or weaker. Which one, guys? Stronger or weaker IMFs? Please know this because you're hesitating and that scares me. If this is the most polar, are its intermolecular forces stronger or weaker? Stronger. You're all good on that, right? But guys, that's exactly right, Ami, where we're going. We are then going to talk about, does that mean that it boils at a higher or lower temperature? Does that mean that it evaporates volatility more or less easily? Does it have stronger or weaker cohesive forces? Stronger or weaker adhesive forces? And that's where we're going. So in this homework assignment, you identified polarity. Polarity leads to stickiness. Stickiness leads to all sorts of other stuff. So guys, any questions on 1 through 3? Can I ask you this question? How did you know, and it's not even represented on this paper, the screen, how did you know which one was more polar? What did you have to do? Yeah.
You had to look at all the atoms that were bound around the central.
And what did we look at about those atoms?
The different electrons.
Beautiful. So guys, in order to do this, and I don't even know the numbers, but remember what you did. You needed to look up the electronegativities of these atoms, and then what did you do with those electronegativity numbers? Subtracted them. And once you subtracted those electronegativity numbers, that then told you the polarities of the bonds, and then you just found the molecule that had the biggest differences in electronegativity, therefore the most polar bonds, and that told you the most polar molecule. Is that clear as well? Okay, so guys, were you good on one? They don't even have numbers, right? The first three, were you good? Okay, so then guys, an apology. I don't know what's going on, but down here on number 6, these are carbons, and then there are hydrogens all the way around this. I don't know why they're not printing, but I can't get it fixed. So functionally what you're looking at is something that looks like this. Only here you've got a carbon double bonded to an oxygen, which made a huge mess. But that's the idea. So guys, make sure you're building on a firm foundation. The homework that you're going to do today relies upon you getting these right. Page 3 in the homework assignment is all about you getting these right. So guys, as you're checking your homework assignment, make sure you're circling the right examples, the right molecules, and make sure your Lewis dot structures are good. You guys all good? Do you need anything? Go ahead, David.
So for number 6,
Yeah.
that acetone was no polar.
Okay.
I was just thinking of the carbons that
Yeah.
have 3 hydrogen. On their angle, it's going to be pushing the carbon upwards.
Yeah. Yeah.
And the carbon is attracted to the oxygen, so that is just...
Yeah, let me talk to that, because you're not wrong. So, guys, you understand that this is a general chemistry class, right? And so, guys, this class does not even begin to represent even a freshman chemistry class in college. If you want that experience, and I pray that some of you do, come take AP from me next year. David, you're actually, I don't want to say you're right, because then that's going to make people think that I'm teaching them wrong stuff. Let me leave it at this. This is actually way more complicated than what we're doing. As a matter of fact, it's only been in the last 20 or 30 years that we've actually had computers that are fast enough to do the math to actually model what's really going on here. So let's talk about how we're going to do this, and then let's talk about why what we're doing isn't quite complete. Okay? So what we're doing is this. We're drawing in these polarity arrows, and we're doing that by following flow, right? And so those are all carbons. So these bonds are not polar. They're carbon to carbon, so they're just we're going to consider them to be non-polar. So the only bond that we really need to think about is polarity, which is this bond, and we can measure its polarity by subtracting electronegativities, right? Then here what we're doing is we're looking at these two bonds, and so what we're doing to figure out polarity is we're only looking at the bonds that neighbor the overall polarity arrow. So for this one, we're just looking at these. For this one, we're only looking at this. And so the difference is that this hydrogen, which is with its relatively low electronegativity, it's the weakest guy in the block. If we've got carbon, oxygen, and hydrogen, hydrogen is the weakest dude in the neighborhood. And as a result, this bond right here is the most polar bond between this one and this one and this one. That's the most polar bond, making this the most polar molecule. Does that make sense? Do the math if you're not. Well, let's not do the math now, but that's the case. So if we look at their electronegativity differences and subtract, you would find that this bond right here has the greatest difference in electronegativity because hydrogen is the weakest element of all the elements that we're looking at, and as a result, it forms the most polar bond. And so what we do to figure out the overall polarity of a molecule is we only look at the bonds that are neighboring the overall polarity arrow, and we subtract, and then the one that's got the molecule with the biggest numbers, the polarity, is then the molecule that's most polar. You okay with that? Okay, here's why what we're doing is not quite complete. And David, what you're saying is actually what we're disregarding is molecular shape. So we take into account molecular shape because that sort of drives where we draw the overall arrow. But the difference is this. What we're doing is we're ignoring all of this. And we're ignoring this, and we're ignoring that. And we're also ignoring the way these things orient to the overall molecule, and that's not okay. But in order to take those things into consideration, it involves modeling that's way beyond anything we'll ever do, and so we're not going to go there. Okay, so for us, draw in the overall polarity arrows, do the subtraction, the one with the greatest difference in electronegativity, most polar, that's your guy. Circle it, that's your most polar molecule. Is that okay? You guys okay? Great questions. Are we good? All right. So guys, let's do this. While you are grabbing note-taking materials, you don't even need periodic table. You know what? If you really wanted to, guys, you could even grab the notes that you started last time and just pick up there if you'd like. Actually, you're going to see that's where I'm going to start. So if you just, you know what? Let's just do that. Grab your notes from last time and let's just start there. I am going to pause. All right, we're ready. Hey, so guys, do this with me. You'll notice that when we graded homework, we talked about why it was important to know which one of those molecules you circled. So guys, follow my hands, follow the journey, because here's where we are. Last time in class, we said molecules are polar. And then we talked about all molecules don't have the same polarity. Some are more polar than others. Those were the ones that you were circling. And we just did a really deep dive on knowing how to know which ones to circle, because you subtract the electronegativities of the bonds next to the arrow. The ones with the biggest differences are the most polar molecules. You guys clear on that? Okay, then we said this. We said these molecules that are the most polar are the most magnetic, the stickiest, and they're the ones that stick together the most, but we don't call it sticky, we call them IMFs. You guys with me there? Okay, so guys, this then is the next step. We're going to do the so whats. So what? What does that mean that a molecule is or isn't sticky? How does it change its behavior? And guys, that's what we're doing today. To get us started, you guys should have these in your notes. So guys, find this place in your notes. You all got it? So guys, if you were not here last time, guys, I would encourage you quickly to scratch down these Lewis dot structures. I'll pause for a second. Well, let me just ask, was anyone gone last time that does need to do that? I think you were all here, right? Okay, so guys, this then is where we're at. We drew Lewis dot structures, we identified polarities, and then we identified which one was the least polar, which one was the most polar, and which one's polarity was in the middle. You should then be able to answer this question. Left, middle, or right? And guys, I want you to point with your thumb. Left, middle, or right? Which one's stickiest? Y'all going that way? So guys, how do we know that it's this one? And the idea, and I know I'm beating this to death, but guys, the idea is this is the most polar, and therefore it's the stickiest, strongest IMFs. This one is the least polar, and it is the least stickiest, very weak IMFs. And then methanol, this alcohol, will be in the middle. We good? Okay, so guys, be ready to write. So where are we headed next? And the answer is this. Create a subtopic, if you will, in your notes. And please do not write out the words intermolecular forces. Please write IMFs. IMFs and physical properties. So last time in class we went polarity to IMFs. Today it's IMFs to physical properties. So guys, let me explain to you the way today is going to unfold. The beginning of this is going to be super secretarial. You're just going to write down definitions. There are 5 physical properties that you're going to learn about. I'm going to define each one of them for you, and you're just going to write down the definitions. That then becomes our laundry list for the day, and we're actually going to go through each one of these and figure out for CH4, CH3OH, and H2O, we're going to figure out how those things are different based upon their polarities. See where we're going? Here we go. So guys, this is where we're at. Don't write this down. So guys, here's where we are right now. You should be able to agree with all of these ideas. Intermolecular forces are attractions between polar molecules. You're thinking stickiness. Then guys, number 2, the strength of the intermolecular forces depends on how polar the molecule is, and those were all the arrows. Then guys, this is where we're headed today. The strength of these intermolecular forces within a substance determines the physical properties. Now, what are the physical properties we're going to do? The first one, and you're now writing this down, the first one is phase. But guys, you all know the 3 phases of matter, right? Yeah, what are they? Solid, liquid, and gas. Write them down. Solid, liquid, and gas. Guys, those properties depend upon intermolecular forces that depend on polarity. So guys, that's property number 1. Property number 2, and actually the rest of these properties are going to be properties of liquids. So guys, here's the trick. We know that there are 3 phases: solids, liquids, and gases. Those depend upon IMFs. But guys, once we're done with that general idea, we're then going to focus on liquids. So now you're thinking, what about solids and what about gases? Guys, we are not going to do solids in this class. We do talk about the chemistry of solids a little bit in AP, but frankly, they've pulled back from that even in AP classes. If you decide to major in chemistry, you'll do a lot of solids stuff about your junior year. But understand, we're not going to do a lot with solids in this class. So then the question is, what about gases? Guys, gases are really important and really interesting, and it's actually the last unit that we do in the year. So we're not going to talk much more about gases until like late April. We're not going to talk about solids ever. So the rest of the stuff that we're going to do are the properties of liquids. And the first one is what is called volatility. So guys, a lot of you probably have heard of the word volatility because we're increasingly becoming a society that thinks about mental health and things like that. And if you have a friend, or maybe if you are a volatile person, you're somebody that's very prone to just kind of exploding. That is not what this means. Volatile in this setting means prone to change. And specifically when we say prone to change, we mean prone to evaporate. So guys, if you have a liquid that is very, very volatile, it's a liquid that evaporates really easily. So it's kind of like the difference between nail polish remover and olive oil. Guys, I don't know if you've ever, you spill olive oil in your kitchen and you got to clean it up because it's never going to evaporate, right? It's going to be there for stinking ever. But guys, if you've ever been around somebody that's doing their nails, like Jessica's upstairs, like taking the polish off of her fingers, and like you can't even be on the second floor because of all of the vapors. Guys, nail polish remover is very volatile. It evaporates like crazy, but cooking oil, olive oil, doesn't. That's what we're thinking about when we think volatility. Then guys, the next one we're going to do is boiling point. Boiling point is the temperature at which a liquid has enough energy to become a gas. That's all boiling is turning a liquid into a gas. And so the boiling point is the temperature at which this happens. Guys, we got 2 more. There are 2 more properties that we're going to talk about. The next one is cohesion. When you think about cohesion, think about the word cooperate. And when you're cooperating with a group, you're working well within a group. It doesn't mean you're working well with other groups. It means you're working well within the group. And so guys, when you think cohesion, think cooperate. These are forces of attraction within a substance. The important part is within. Then guys, the final thing that we're going to talk about to wrap up our day is adhesion. When you think about adhesion, think about adhesives. And adhesives, we have another term for, we call them glue. So guys, when you think adhesion, think adhesive, think glue. And what does glue do? Well, it sticks two things together that are not the same. So these are attractive forces between two different substances in the same way that glue sticks two different things together. So guys, I see you sort of craning your neck, so let me zoom into that. So guys, this then lays out for us what we're doing for the rest of the day. Things are about to get visual. Things are about to get interactive. Things are about to get messy. Kind of describes our lives right now. Visual, interactive, and messy. But guys, in all seriousness, this lays out what we're going to be doing today. We're going to now look at the molecules that we drew the Lewis dot structures for previously, and we are going to figure out, based on their polarity and therefore their intermolecular forces, are they sticky? Do they boil at high or low temperatures? Are they solids, liquids, or gases? We're going to figure out all of these things based upon their structures and polarities. So guys, you ready to go? This is going to go fast. Are you ready? Okay, here we go. So guys, the first one that we're going to do is phases of matter. So guys, just write down phase. Again, reviewing solids, liquids, and gases. The phases of matter are solids, liquids, and gases. So guys, do not write what I'm about to throw up on the screen down. Let me just say this. The only things that you are going to write down from here on out are the things that show up in blue. Okay, I wasn't sure if I made them blue or red. But guys, from here on, the only things that you're going to write down are the things that come up in blue. Agreed? Okay, so guys, the first thing we're going to talk about is CH4. Find it in your notes from last time. CH4. You see it? Is it symmetrical?
Yes.
Is it polar?
No.
Does it look like this?
Yes.
Yeah, okay. So guys, are these molecules sticky? No, why not? They're not polar. So guys, these molecules are not sticky. As a result, they do not attract to each other. So guys, if you get a whole bunch of these molecules together in a container, will they stick together? No. So what will they do instead? Let me show you. Guys, do any of you know what CH4 is? It's actually methane. It's Bunsen burner gas. So guys, literally, when I do this and open up the Bunsen burner tap, billions of these molecules are flying out of the tap and they're flying into the room. And when they come out of the tap and fly into the room, do they stick together and does it rain? No, what do? They fly out into the room and they spread out in which phase? They're a gas. So guys, why is methane a gas? Fundamentally, what makes these molecules a gas? They're not polar. And because they're not polar, do they have intermolecular forces? No. And if they don't have intermolecular forces, they don't stick together and therefore they're a gas. Get the idea? So guys, tell me other substances that you know that are gases. Oxygen. Guys, oxygen is a gas. Why is oxygen a gas? Does it have IMFs? No. And if it doesn't have intermolecular forces, is oxygen polar? Can you guys, and this is where this gets in. Where's my other molecule?
It's right here behind that.
So, guys, I know that you're sitting here going, wait a minute, he's throwing crap around the room and what's going on, because you got to understand the idea. Do this with me. Is oxygen a gas? Obviously, yes. Because don't miss this. Is oxygen sticky? How do you know? Because it's a gas. So guys, if oxygen is a gas, we know that it's not sticky, because it spreads out. It's a gas. So what do we know to be true of oxygen if it's not sticky? Is it polar? No, and therefore it's symmetrical. Guys, it actually looks, did I not build, oh, I didn't build 2. Oh, I want 2. That's all right. Guys, this is what oxygen looks like. When we breathe oxygen, oxygen molecules look like this. It's O2. There's 2 of them bonded together. Is this symmetrical? Is it polar? Is it sticky? No, oxygen's a gas. Does that make sense? But guys, do you understand that when you breathe air, most of it is not oxygen? What is most of the air we breathe? 70% nitrogen. Looks like this. Ready? Is nitrogen a gas? Yeah, we're breathing it. So guys, let's talk about why. Nitrogen is a gas. Is it sticky? No. Is it polar? No. Is it symmetrical? Yeah, do you get the idea? So guys, any molecule that you know to be a gas is not sticky. That's why it's a gas. And if it's a gas, it's not sticky. And if it's not sticky, it's not polar. And therefore, it's a symmetrical. Do you get that idea? That's it. That's important. Good? Okay, so guys, what about carbon dioxide? Also a gas, right? It's a greenhouse gas. Because it looks like this. Is carbon dioxide a gas? Yes. Is it sticky? No. Why is it not sticky? Because it's not polar. And the reason it's not polar, it's symmetrical. Guys, do this in your notes. Would you please write a sentence to yourself that helps you make sense of that? What is the driving? So do this. What makes a substance a gas? Write a sentence to yourself. What makes a substance a gas? So guys, normally what I'd like to do is have you read your sentences to each other, but because of all the time that we spent figuring out our COVID life, we're not going to have time to do that. I would love to talk about them, but we're not going to share together. Kaisen, go ahead. In case of what? No, you're okay. Yeah, good. Uh-huh. Yeah. So let's say this. When we say a substance is a gas, we mean at room temperature. So you're absolutely right that we can take water and we can boil it and turn it into a gas. But understand that takes energy to overcome the stickiness. So when we say a gas, we mean at room temperature. Okay. So guys, did you do this in your sentence? The question was, what makes a substance a gas? Did you mention that it's not sticky? And we call sticky IMFs. And did you mention the reason that it's not sticky is because it's not polar? If you don't have non-polar in there, you need to include it. And then guys, did you also mention to yourself that it's not polar because it's symmetrical? You've got to have those ideas. Guys, this is the way I summarized it. If a molecule has no polarity, therefore it has no IMFs, therefore it's a gas. And then you probably put a previous statement to this that says it's symmetrical. But guys, that's last time's material, so I didn't include it in today's notes. But that's the full thought. Not symmetrical, not polar. Not polar, not sticky, it's a gas. Good? Yeah.
I know this doesn't have to do with what you specifically talked about.
Okay.
Couldn't they be sticky when involving other molecules? Could be different, like for this case, negative, because the outside is all positive, it's hydrogen.
Yeah, so David, that's really interesting that your head is going there, and the answer is sometimes. But what you're now talking about, for the most part, is solution formation. You're talking about different substances interacting with each other, like things dissolving in water. The thing that's interesting is something that's not polar doesn't dissolve in water, because water is polar and this is not polar, and there's nowhere for them to attract, and therefore it doesn't dissolve. This, on the other hand, does dissolve in water because this is polar and this is polar, and that polarity attraction between intermolecular forces causes this to dissolve. And that's actually where we're headed, who knows when. Could be in April, the rate we're going. But it's how we're going to wrap up this unit. So your head is going in a good place, good direction. You guys good? Okay, so let's do this then. Guys, shifting gears, again, this is not in blue, so don't write it down. Guys, same game with CH3 or CH3OH. Ready, guys? Is this symmetrical? No. Is it polar?
Yes.
Is it sticky?
Yes.
Will it fly apart? No. So will it be a gas? No. So what will it be? Yeah, and guys, it actually is. When these all get together, it turns into this. And guys, in your little world, anything that looks like this is water. But guys, there is absolutely no water inside this jar. The only thing inside this jar is these alcohol molecules. Fortunately, you drink it and you go blind. But guys, the only thing inside of here are these molecules, and these molecules are attracting each other, positive to negative dipole, and they all stick together and it looks like this. Again, guys, there's no water in here. The only thing that's in here is these. Do you get the idea? So what then is the big idea? Can you agree with this? If a molecule is polar, therefore it will have IMFs. It's sticky, and therefore it will be a liquid. Does that sit okay? If it's polar, therefore it has IMFs. It's sticky. If that's the case, they stick together and they're not a gas, they're a liquid. Can we break those IMFs? Sure, that's called boiling or evaporation, which is where we're headed next. But that's the idea. So guys, this then is the general principle. What do we now know about any substance that is a liquid? If a substance is a liquid, is it sticky? If it's sticky, is it polar? Yeah. Guys, what's another substance that we know to be a liquid? Water. Aha. Same principle, guys. Water is polar, therefore sticky, therefore a liquid. And guys, we see that here. These molecules are polar, therefore sticky, therefore a liquid. And these all get together. And literally, guys, this is what it looks like inside a bottle of water, because all these molecules are stuck together because they're sticky, because they're polar. Beauty? Okay, so guys, what now is sort of the obvious question that I already told you we're not going to talk about? What about solids? Well, guys, we're not going to do a lot with that now, but we will say this. If intermolecular forces hold molecules together to be liquids because they're polar, what's got to be true of the polarity of something that locks together as a solid? Superpolar. And guys, that is actually the case, but we're not going to dig into that right now. There are some other things that play a factor in that, including molecular size. We're not going to deal with it in here, but guys, understand that these trends do carry through to solids. We're just not going to muck with it. So are we good on these ideas? So let's make sure we're clear. Guys, if something is a gas, is it polar? No. If something is a liquid, is it polar? Yeah. If something is a solid, is it polar? Yeah, even more polar, but we're not going to go there. So guys, are you with me up to here? Okay, so now we are going to stop talking about gases and we're going to stop talking about solids and we're only going to talk about liquids. And because that's the case, we're going to get rid of the CH4 and we're going to get rid of the nitrogen and we're going to get rid of the carbon dioxide and the oxygen. And guys, the only things that we need now are liquids, which are going to be water and which are going to be methanol. And so now we're going to play around with these guys. And guys, the first one we're going to talk about is volatility. Write this down in your notes, even though it's not blue. I should say you're going to write down the headings and then only write down the stuff in blue. So guys, let's do this. In order to talk, well, let's remind ourselves, what is volatility all about? Check your notes. What's volatility about? Evaporation. So if something is volatile, if it has a high volatility, it evaporates really well. In order to understand this, we got to talk about this. Guys, if this is what water looks like, why are these molecules not evaporating? Well, the reason is because they're all stuck together. And what sticks them together? Intermolecular forces. So these guys are all stuck together. But are they holding still? Do you know what's going on inside of water? It's like a mosh pit in there, guys. These things are flying around at hundreds of miles an hour, running into each other, running into the walls of the container. But guys, every now and then one of these molecules gets to the very surface of the water, and it's got just enough energy to break the intermolecular forces, and it goes woohoo, and it jumps out, and we call that evaporation. Understand, though, guys, that not all of the molecules have enough energy to do that. Only some of them do. So the molecules that have enough energy to evaporate, they come to the surface and they jump out and they evaporate and they take their energy with them. Do you guys understand that's why we sweat? Think about that. Guys, imagine if we sweat and now our skin is covered with water, right? And what happens to that? Well, why do we sweat? What's our body trying to do? Cool itself down. So these molecules are sitting here on our skin, and as these molecules evaporate, the ones that evaporate are the ones that have enough energy to break the IMFs. And the ones that have enough energy to break the IMFs go away, and they take their energy with them, and the ones that are left behind have less energy, and that cools us down. So, guys, the question then becomes this. First of all, let's make clear. Are you okay with the idea that in order to evaporate, you've got to break the intermolecular forces? Is that okay? All right. Then, guys, do this with me. Think about water and think about methanol. Ready? Guys, watching these molecules, you got to think about this. This is tricky. So here we go. Water, methanol. Which one's more polar? Water. Water is more polar. So if water is more polar, will its IMFs be stronger or weaker? Stronger. So if the IMFs are stronger, will they be harder or easier to break? Harder to break. So guys, which one will be harder to evaporate? The water or the alcohol? The water. So guys, let's do that again. Water is more polar, it's stickier. If it's stickier, it's harder to break apart. If it's harder to break apart, it's harder to evaporate. If it's harder to evaporate, it won't evaporate as well. And guys, I'm going to demonstrate that to you right now. So guys, I'm going to make a puddle of, feel free to stand up if you want to watch. Guys, I'm going to make a puddle of water right here. And I'm going to make a similarly sized puddle of alcohol right here. Now, guys, you understand that inside those puddles, we literally have this. We have a puddle of molecules. It's not a molecule thick, but we have a puddle of molecules, and some of these have enough energy that they can jump out and they can evaporate, right? But the same thing's going on over here. We have a puddle of molecules, and some of them have enough energy to jump out and evaporate. Now, what do you know about the attraction inside this stuff? Stronger or weaker? It's weaker, right? So it will evaporate more or less easily. Weird question. More easily. Easier. Thank you. So guys, I can show that to you. We're going to speed this up a little bit. The way we're going to speed this up is by spreading these out. You guys, I don't know if you can see this. Feel free to stand up if you need to. Can you guys see the alcohol evaporate? Even from where you are? Can you guys not see that from where you are? I can actually see it evaporating. Like just this wet spot, I can just see it go away. And guys, as I spread these out, I can watch this alcohol evaporate. But guys, this water's not going anywhere. Can you guys see that from where you're at? Feel free to stand up if you'd like. But guys, what you're going to see is in about 30 more seconds, this is going to be completely dry, and I'm going to have to clean this up at the end of the day because this is going to be wet second period. So guys, here, let me do this once more. Guys, can you see that? It's gone, like it's almost gone, and this is still soaking wet. So guys, why did this evaporate more quickly? Weaker IMFs. Why weaker IMFs? less polar, and as a result, it evaporates more quickly. So guys, what's the relationship? And it's this. The lower the polarity, write this down. It's now in red and not blue. Sorry, I thought some of these were in red. Write this down. So guys, lower polarity, therefore lower IMFs, therefore higher volatility. Uh-oh. Now the arrows are going in opposite directions. By the way, guys, this is completely dry now. So guys, lower polarity, weaker IMFs. We established that before, but now we know that's going to be more volatile. It evaporates more easily. What a mess. Then guys, the other is true as well. Higher polarities, stronger IMFs, lower volatilities. You guys good on that idea? Can I go on? So we're good on volatility. The higher the volatility, the easier something evaporates, the less polar it is, and that means weaker IMFs. Is that good? Okay. So now, guys, I'm going to move forward, but I'm not sure if you guys are okay. Is it okay if, does anyone need me to wait? You're okay? Okay. Now, guys, as you're writing these things down in red and blue, do you understand that these arrows that you're drawing are the same arrows that you're going to draw to complete your homework assignment? See how this all fits together? Almost as if, Miss Collin, I know what we're doing. I know. You guys okay? All right, guys, the next one we're going to do is boiling. So I know that I've already given you a definition for boiling, but you may have found it confusing, so let's talk. Guys, turn our attention back. You can write down boiling point. Guys, turn our attention back to water. Amazingly, we're almost done. Turn your attention back here to water. What are these molecules doing inside of here? Chaos, right? Every now and then, one of these molecules has enough energy to jump out, and what do we call that? Evaporation. But guys, what if we give this water more energy by sticking it on a Bunsen burner? When we put this on a Bunsen burner, what's going to happen to the molecules? They speed up. More energy makes them go faster. And eventually, all of the molecules have enough energy to break the intermolecular forces and jump out the top. And we call that boiling. Do you understand the difference? Evaporation is onesies and twosies coming out the top. Boiling is all of them have enough energy to jump out of the top. And they're just waiting their turn to get to the surface. Do you see the difference? So do this with me, guys. Let's bring back our method. Let's bring back our alcohol. So guys, let's talk about this. Which one of these is more polar, the water or the alcohol? The water. So the water is more tightly bound together. So will it be easier or harder to boil? Harder. And here, guys, don't write this down, but here are the numbers. Water boils at 100 degrees Celsius. Will the alcohol boil at a higher or lower temperature if it's less polar and therefore less sticky? At a lower temperature, and as a matter of fact, it's about half. This boils at 65 Celsius. Understand that's Celsius. That's still hot. Like a hot tub is about 40 Celsius. So it's still hot, but it's not boiling water hot. So guys, why does this boil at a lower temperature? And again, the relationship is this. Higher polarity, higher IMFs, higher boiling point. That's water. Lower, oh shoot, sorry. I thought I animated the other, but I didn't. So higher polarity, higher IMFs, higher boiling point. Can I give you guys an additional homework assignment over our 5-day break? Because this is distance learning. Here's what I want you to do. As you're just out wandering around sometime in the next 5 days, just look at something that's a liquid and then ask yourself this question. Is that stuff polar? Can you do that as a homework assignment? And then we'll say we had a productive 5 days. Okay. Because that's like applications of chemistry. Last one. Adhesion and cohesion. Last two. So guys, we're going to do these together. But if this is helpful for you, just a reminder, adhesion is between like glue. Cohesion is within like cooperate. So guys, I'm going to show you some pictures. These are not perfect simply because the colors are wrong. But they were frankly the best representation I could show you, and so these are the ones we're going to use. Guys, don't draw the pictures, but that's a graduated cylinder. You guys learned months ago that when we put water in a graduated cylinder, it makes a dip. Do we measure from the top or the bottom of the dip? The bottom of the dip. What do we call that dip? Do any of you remember? The meniscus. Guys, why does water form a meniscus in a graduated cylinder? And the reason is this. Unfortunately, they made the oxygens blue and the hydrogens white, which is not the accepted convention. But guys, what they're doing in this picture, let me grab a writing tool. Guys, what they're doing in this picture is they are actually zooming in at the interface where the glass of the cylinder meets the water. But guys, what do we know about water molecules? They're sticky. And guess what? Glass is sticky. How do we know that glass particles are sticky? It's a solid, right? So guys, the idea here is the glass is sticky and the water is sticky, and in between the glass and the water, those stickies draw the water up the side of the glass. Is that adhesion or cohesion? It's adhesion because it's in between the water and the glass. So guys, the meniscus is caused by the adhesive force between the water and the glass. Now guys, what about this? What if we took the water out of the graduated cylinder, and what if we filled it with alcohol? Is alcohol more or less sticky? Less sticky. So what would that do to the meniscus? It would be flatter. The water would not be drawn, or the alcohol would not be drawn up the sides of the cylinder as much because it's less sticky, and the hump would be flatter. The dip would be flatter. Do you get the idea? Okay. So guys, that would be, as we said, adhesion. But what about this? You guys ever seen this? Bugs that walk on water? Guys, understand, and these are called water striders. Guys, water striders are more dense than water. They do not float. This water strider is not floating on the water. They actually sink in water. So what is it that's allowing this water strider to walk on the water? It's actually fascinating, guys. The water molecules, we've already established this, right? The water molecules are all attracted to each other. That creates a skin on the surface of the water. And literally the water strider because it's light enough, it's actually able to walk on the skin that's on the water because all the water molecules are attracted to each other. Do you guys know the name of that skin? It's called surface tension. And so guys, the idea is that this water strider is not floating. It's literally walking on the skin that's on the water because all the molecules are attracted to each other, and that creates a skin that we call surface tension. Is that adhesion or cohesion? That's cohesion. Now guys, the idea is this. Could a water strider walk on alcohol? And the answer is no. Because these molecules are less polar, therefore the surface tension is weaker, and therefore the water strider couldn't walk on here. That'd be fun to try. It'd be bad if you're the water strider, but still, it'd be kind of fun to try. So guys, the relationship then is this. Higher polarities, higher IMFs. We're not going to do the pledge. Higher adhesive and cohesive forces. So guys, as you're wrapping, Jasmine, please.
So if it goes underwater,
Yeah?
it'd be harder to get out of the water.
Because it'd be harder to reach through the surface?
Yeah.
Well, but realize that if you stick your hand in a cup of water, you're breaking the surface tension just by getting your hand in there. So we're not even aware of it.
But the water spreader can't break the surface tension. So if it's under it, and if it's
Oh, is it also hard to get back up through? Absolutely. That's an interesting question. He's like, let me out, let me out. Yeah, absolutely. The problem is that he can't float in the first place and he goes to the bottom. Yeah, so don't do this, but do you understand that we can actually break the surface tension? You guys, don't pack up. Do you understand that we can actually break the surface tension in water? That's what soap does. So if you were to put a drop of soap in that water, the surface tension would break and the bug would go right to the bottom. It's also polluting. But that's what soap does, is actually disrupts the surface tension. Guys, I know you're anxious. Don't. I still have you for 5 minutes. So guys, let's wrap up the day. This is me wanting you to be successful. Guys, this is what you're going to do for homework. The first thing that you're going to do is you're going to wrap up page 1. You are going to do that by filling in all the arrows that you didn't fill in previously. Then guys, you're going to go to page 3 in the homework. Please do the first one with me. This is how to approach this. On page 3 it says this. Regarding set 1, which will have stronger cohesive forces. Guys, think through this with me. Watch my hands if nothing else. If you've got something with strong cohesive forces, are the IMFs strong or weak? Strong. If the IMFs are strong, is the polarity high or low? High. So what we're saying is, in set 1, we want to know the one that's most polar. And we've already identified that the one that is most polar in set 1 from page 2, do you see the connections? Is the methyl chloride. So when you go to answer this question, you will say methyl chloride will be the most cohesive because it's the most strongest IMFs, because it's the most polar. Do you see that? Again, methyl chloride, strongest cohesive forces because it's the most polar, making it the strongest IMFs. So guys, that's our day. Thank you for being as flexible as you guys are with all the COVID crazies. Guys, we're going to get through this together. Hang on, I still got you. Guys, we're going to get through this together. Please communicate with me as you need, and do that with all of your teachers. Because we can't help if we don't know, and we're not going to help if you don't help us help you by communicating in advance. Communicate with your teachers. Have a great 5 days. Stay healthy. Please, as much as you can, try to protect yourself so that we can come back on Wednesday and we can all throw negative tests and we can all get back to what we do. So guys, we're going to go with the bell rings. Don't line up at the door because that makes me grumpy. And we'll see you next Thursday.